All right, we are back with another quantum physics introduction video. This one should be a quick one. I think last time I said that we were going to be talking about the harmonic oscillator, but I changed my mind and decided to do the free particle instead. So we'll be, covering that hopefully pretty quickly. It's not too much to cover. The free particle seems at face value to be like the most trivial example. But there's some challenges that we'll see shortly. So the free particle, if I go back to my writing, you'll notice I'm not using OneNote anymore as my university subscription did run out to Microsoft Office. And it has been a while since I've drawn with my little writing tablet. So apologies for any mistakes that I might make. But the free particle, of course, is very similar to the previous example of the infinite square well, except it's simply the potential is zero everywhere, rather than just in a square well. So, it's just a particle going around, pretty self-explanatory, all things considered. So if we have our equation then that we write out, we have the negative h bar squared over 2m, and then we're just going to be working, of course, in one dimension for now. We have the second derivative, and then we have, of course, our energy. So, right, normally in the Schrodinger equation, there would be this potential term, but the potential is zero everywhere because that's what we're defining the free particle as. And so we can simplify this sum by using the notation k, which is pretty common. So if we, this has also come up before, if we simply say k is equal to square root of 2me over h bar, this allows us to make the differential equation a lot, my little tablet is moving, a lot simpler to look at, just, simplifying all the constants, right? Because h bar, m, and all that stuff is just some number that we have, and we don't want to, deal with carrying that around in all of our equations. We can reduce it to the second derivative of our function is equal to negative k squared times our function. So this has become a much more straightforward differential equation to look at, and is really not that hard to postulate a solution for, or put forth a solution for. So let's see if we can do that. Well, we can see, okay, the second derivative is equal to that with something squared in front of it. That looks a lot like an exponential, right? If we have the second derivative, I'll just do f double prime of e to the negative x, we'll get, I'll put negative 2 for simple. The first derivative would be negative 2 e to the x, negative 2x. Second derivative would be 4, or negative 2 squared. So you can see that this is sort of an appealing format for this. So we can write this out, the solution here as, once again, just putting constants for now in here, a e to the negative, negative will be the next one, a e to the I kx plus b e to the negative I kx. So you can also sort of interpret this in sines and cosines as we did in the previous example with the infinite square well, where we wrote this, as the final equation was, sine of n pi x over L or something like that. And so sine and cosine, right, e to the I theta is cosine plus I sine. And so there's this interchangeability here. We're going to be writing this in exponential form for a reason you'll see shortly. And part of that is because we don't have any boundary conditions. If you remember in the last video or 2 videos ago, we were able to find out a solution because we could say, okay, now let's set it equal to 0 at our boundaries of the square well. And that's how we go about solving it. There are no boundary conditions here. And so we can't restrict the values of k, as we did previously, to integer multiples of real or positive whole numbers. But in this case, we have particles that can carry any positive energy. So let's just add now our, fortunately I can't scroll, so I have to do a new page. But let's tack on our time dependence, right? Previously that was just a function of x. Now let's integrate. I'm sorry, I shouldn't say integrate because that's a mathematical term. I just meant to incorporate our time dependence. So now we have our function of x and time. Once again, this is our one-dimensional free particle. And we have the same a. I don't know why there's little dots. I don't know if I can. I'm still figuring out. I think that's new. But we have our I, k. And here we're just going to have our x. And then if you remember previously, as we saw with these sort of time dependence problems, it's almost always just e to the negative I something t, and in this case this something is just the h over 2m k, h bar, sorry, k over 2. That's really annoying, those little dots. And so this time dependence was something that was discussed much more in previous videos, and we can see that when we're it's often left off when we're doing sort of textbook problems, because when you're trying to find some, x position operator, they just integrate out. When they multiplied by the conjugate, the negative exponent becomes a positive, and so that's sort of why you'll often see them ignored in textbook problems. And then we have the b, of course. Over here we have just the same thing, negative I k x. Here we have plus because we have took the minus sign out of this, h bar k over 2m t. Those little dots are so annoying for me. Maybe they're fine for you. And so yeah, we have now this equation that represents our wave function. It's a function of position and of time. But now we want to do a little more analysis of this. Specifically, we know that in this equation we have a wave, right? Because as I said, these are just sines and cosines with a lot of extra steps. So if we're saying, okay, this is a wave function in the sense that it literally represents a wave, and when I'm saying wave here, I'm aware that the term is called a wave function, but also that this represents a wave of unchanging shape traveling in a certain direction. So if we have, x plus or minus some variation of t, we can see that this is a wave of unchanging shape moving in a direction in the opposite, right? So if we have a plus, it's moving in the negative direction. And so this is important for understanding what's going on here and what our next step is going to be. I just want to also interrupt here and say, of course, that I believe I mentioned this in the first video, but I think it's important to give proper credit, because I am just, I'm not writing these equations out of thin air. I'm taking them from books that I'm working on. The two books, just to always cite the sources, are Quantum Physics: A Fundamental Approach to Modern Physics by John Towson, and Introduction to Quantum Mechanics, 3rd edition by David J. Griffiths. So if you're looking for more equations and more justifications, you're welcome to check out those books. I just want to interject there because now that I'm thinking about it, I really want to make sure that I don't try to steal credit for these equations or this way of presenting the material. And so moving on from that, what we have is, as I said, the wave is unchanging. So if we have our our change here, x plus n of t, this is going to be some constant. This is just you know, if you think about our little sine wave, not a great drawing, but as we saw before, here to here, here to here, here to here, this is all the same, right? This is a constant, and that for the case of sine, that value is 1. And since our wave, right, if we think of this as moving and as progress, our wave has uniform velocity, meaning that the shape doesn't change. So we can combine our equation and just say, okay, let's write, here we do sub k, where k is either going to be, as we saw before, k was square root of 2me over h bar. Here we're just adding a plus or minus, and we're just going to combine it and say a e to the I k x minus h bar k squared. You can see we're integrating the k into the parentheses now, 2mt. And so when k is positive, when this is a positive value, then we can see that it's traveling to the right. When this is a negative value, this is traveling to the left. So the state of our particle, of our free particle, is a wave, and a wave that looks like it's moving, right? I'm talking about, is it moving right or left? And so, of course, this ties back into something I don't believe I've touched on before, but is common as like the first thing you do is calculate de Broglie wavelengths and stuff like that. And so we're not going to actually touch on the de Broglie formula right now. That just can be used to ascribe wavelengths and stuff to the particles that we're talking about. But if you want to know more, there's often a connection that's made here. So moving on, we can see one thing that might be noticeable is that when we do our normalization, this, you know, we want to figure out what A is. So let's make a new, actually, I can probably do it right down here. So we want to figure out what A is. So as you might remember, we just integrate. So we do our integral from negative infinity to infinity over psi star. This is, of course, a function of x and t with k there over all x. And so then we say this should equal a squared. And then the integral here, if you notice, it's going to be of nothing, right? We'll have e to the I, and then we'll just call this, you know, v for now. We can just represent this as v, as anything. So we have e to the iv, and then we have the star, which is e to the negative iv. These cancel out. That's just 1. So this becomes 1, negative infinity to infinity dx. This becomes a squared infinity. And now we're left with saying, how do we make this normalized? And the easy answer, of course, is, well, there's an infinity there. You're not going to be able to normalize it. So this is not a normalizable state that I just proposed for us. And so it's important to recognize that the solutions do not represent real states. The solutions that I just wrote down are not real states, and so that has an important and interesting interpretation in the sense that, okay, we started off with saying there's a free particle with no, just vibing around, and now I said, well, the solution doesn't have physically realizable, the wave function that I gave as a solution isn't physically realizable. So what does that mean? Well, that means that you don't have a free particle with a definite energy. And that's the interpretation here. When I'm saying that these are not realizable. They don't exist in a stationary manner. And so that's why I say definite. We'll get more into uncertainty in the future. I believe I haven't covered much on that. And next time might be harmonic oscillator or position and momentum and generalized uncertainty principles. But for now, we'll just leave it at that. We're saying that this particle doesn't have a stationary state and won't have a definite energy. And so there's some further interpretations that we can do here. Specifically, we can represent these separable solutions and understanding their understanding of physical interpretation. So if we basically do the Fourier transform of this, you'll notice it looks amenable to that, the e to the ik. Xt is very amenable to a Fourier transform. We get a range of k's, not just a specific value. And so you'll often see this called a wave packet. And so you'll often see, if I can draw this out, let's see if I can draw this. Yeah, there we go. That's often that's my best drawing approximation of a wave packet. So this envelope represents the group. Oh, I should specify. I realized I wasn't drawing there. This is the envelope here. This you can sort of see it envelops it, hence the name. This is the envelope of the wave packet. And this whole thing, which is going to be moving along, if we consider, if I draw this again, this is not a great drawing, I recognize, but if we consider this again, oh, wow, that's bad. There we go. This is moving along. That's what's called the group velocity, and these inside are moving along. That's what's called the phase velocity. And so, when we talk about free particles, you can see why it wasn't the first thing to bring up. There's something very unappealing to, or pedagogically unappealing about having our first example not even be real, in the sense that there's no, our solution to the Schrodinger equation says, hey, this doesn't exist in a stationary manner. Only by looking at the evolution of these wave packets can we really achieve any analysis. And so that is what is often done, is you can look and you can calculate these velocities for phase and group velocities. And so that's sort of the quick and dirty overview of this free particle. Hopefully you got some insight there. I skipped a lot of things. I recognize that. I didn't even write out the Fourier transform or anything, because I believe the most important part is the high levels in this section. In the previous one with the infinite square well, really getting down to it is important. But the free particle it provides an interesting understanding and discussion of the interpretations, but I don't have as much. I don't believe that there's as much to be had in going through all of the math in this example. And the next one, which will be uncertainty, I believe, maybe simple harmonic oscillators, there will definitely be a lot of nitty-gritty details, especially in the uncertainty one, where you want to, when you're talking about especially like commutation relations, I always believe in doing all of those out by hand. And so, yeah, that's it for now. I guess you could probably tell the next video is on the quantum series is a little TBD, but